So let's get started. We are in for a treat. It is such a pleasure to be introducing Rob Phillips here. I thank Dinesh for introducing me to Rob and his incredible work when Dinesh was arranging this colloquium. So Rob Phillips is the Fred and Nancy Morris Professor of Biophysics, Biology, and Physics at Caltech. He's a fellow of the APS and AAAS. He recently won the Feynman Prize for Excellence in Teaching from Caltech. And all of that was his introduction aimed at the faculty. Now comes the introduction to Rob aimed at the students. You've already gotten a flavor of who Rob is if you've come to his workshop today. But I want to start with the fact that Rob is someone who is where he is through a very roundabout road. If it's okay, I'm going to talk a bit about that. He left high school at grade 11. He did not study in college. He didn't intend to go to college at that time. He learned all of undergrad physics and math, equivalent to the BS, on his own. Over a period of about 7 years, when he was traveling and working odd jobs, including 4 years of being an electrician. And at some point, he was traveling and a random conversation on a train with a person made him realize that, you know, if I want to do the kinds of things I want to do, maybe I do have to go back and at least get a piece of paper that says I have a degree. So then what did he do? He went to the library, the public library, and got a book on how you can get a college degree without actually going to college. So that led him to this program through the University of Minnesota called University Without Walls, which is how he earned his bachelor's. But he did that and finished the bachelor's at the same time that he ended up in grad school without ever actually having the bachelor's or doing college. His first physics class, a formal physics class, was Jackson E&M. So that just tells you the kind of person he is and the kind of reading he must have done as he was working and traveling. So this just blows my mind. He's a superb teacher and a really engaging speaker. He started off in condensed matter theory as a professor at Brown and then moved into biophysics. According to Kevin, has written one of the best books in biophysics, but at Caltech. So anyway, I will stop here. Rob is a unique person and really we're fortunate to have you here. So thank you.
Good afternoon, everyone. It's a great pleasure to be here. I'll never live up to that introduction, but I guess I do have to say that once I have great parents. You know, it's weird to come home to Ivy League parents and tell them you've had enough of high school, but they were super supportive. Anyway, so I don't think I'm pretty torn on the subject of colloquia. And we've had a lot of debates at Caltech. We even thought about ending our colloquium series. You know, just somehow over the last 30 years, I feel that we've eroded in our ability to have talks from different fields where you feel like you go and you don't fall asleep or you don't start calculating or dreaming or whatever after the second slide. So I don't really know how to give a talk. I'm very torn about this. So what I've done, it's just a disclaimer, is I'm not talking to anybody that's a specialist in the fields that I am in. And this is more meant to just try to engage you with why the study of life is really amusing. And more than that, I really decided to tell you about something that I'm very excited about, but it's not done in any sense of the word. So just bear with me, I guess is what I would say. So here's the talk outline. So the first part is really just to set up the notion of how do we think about dynamics writ large across scales, across fields. So I'll spend maybe 10 minutes on that. It's meant to entertain you. and possibly capture your interest. And then the middle part is really the essence of what I want to say, and I can preface it, which is to say that I think that biological systems have a way of doing dynamics, which is not at all the way that dynamics is done in many, many, many of the contexts that we're all used to in physics. And you'll see what I mean as I go along. And in a nutshell, the idea is that often biological systems do exploratory dynamics. Just to preface it, so you can already be thinking about it, the way that dynamics often works in biology is best illustrated by thinking about building a train between Boston and New York. If civil engineers do it, what they'll do is surveyors will come out, they'll figure out where to go, they will buy a certain amount of steel, they'll hire workers, and they'll build 2 tracks and they'll meet in the middle. The way that the cell would do it is it would just start at South Station, at Penn Station. It would just lay down track. It would go for a while, and if the 2 didn't run into each other, it would take it apart and do it again. I literally am telling you that right now that is happening in your body before chromosomes segregate in cell division. Literally, that's what's happening. And I'll show you a video of that, and so you can watch it. It's exploratory dynamics, and it's, in some sense, I think, necessary. And then I will give as an example this concrete example at the end about chromosome segregation. So that's the plan. So let me cut to this idea of stuff, what I like to call stuff of tea. When I teach either graduate biophysics or stat mech, or when I teach freshman biology at Caltech, I always use these words stuff of tea. And what I mean by that is there's something that we're interested in, and we want to find out how it evolves over time. And it doesn't matter what the stuff is. So the way I think of this is this goes back to Galileo. He maybe is the first one that figured out a law of stuff of T. And I always feel kind of a big resentment about this equation, S equals 1/2 GT squared, because how Galileo pulled this off without a stopwatch, without a clock, is actually pretty magnificent. And yet, 1/2 GT squared is about as bad as it gets for plug and chug mentality. We've kind of lost our admiration for how hard it was to figure that out. So I won't bother you with this quote, but I think it's good, clean stuff. But Newton came along, and his version of stuff of T is F equals ma. He showed us how the language of Galileo, projectile motion, and the language of Kepler could be brought under one intellectual roof. This is a figure from the Principia, which I happen to think is one of the great figures ever. And I find it kind of surprising that when Newton proved Kepler's law of equal areas, he did it as shown there. That is literally out of the Principia. And what he did is he showed that 3 triangles have the same area. Blue triangle, pink triangle, green triangle. And what he was doing is saying, let the planet move in a straight line for a little bit. After a time delta t, there's some triangle. And then he says, what I'm going to do next is I'm going to imagine it with another delta t, and that's a second triangle. And then the third triangle is the one that went off, corrected, its direction corrected a little in this direction. And he showed that those 3 triangles were equal. And if you like, in the end, he thought about letting delta t go to 0. But that's, again, I'm not making this crap up. You can just go look for yourself. Another example, I talked about this morning because coming back to this story, when I was 16, I told my mom first that I was going to quit high school. And my dad was a really great guy, but every evening he had 2 JB mists. I'm not a drinker, so I don't really know what a JB mist is, but it's something I think that has scotch in it. And one of the rules was you didn't talk about serious stuff at night. My dad wasn't mean, he wasn't anything, but you always talk to him in the morning. She said, well, make sure tomorrow morning you talk to Dad. So my dad comes into my room, and I said, yeah, I think this is my last year of high school, and I don't think I'll be going to college. And he said, what are you going to do with yourself? And I said, there's this guy, Maxwell, and he wrote down some wave equation for electricity and magnetism, and there was a number that appeared in his equations, which is right here, which is 1 over the square root of what we now call epsilon naught and mu naught. And he plugged in some numbers, and he got the speed of light. And I got to understand what the heck that was all about. Like, what does it mean to have a wave equation? How on earth is it that these 2 numbers that ostensibly have nothing to do with light end up giving you the speed of light. That's literally, and my dad was like, sounds cool, like, go for it. So, so I love this example. Here's another one. So again, what am I doing? I'm trying to convince you that along the way, we thought about mechanics. We thought about electricity and magnetism. Over in the world of chemistry at the same time, the law of mass action is coming into play. And if you like, then you can think about spatial examples too. So now it's stuff of position and of time. This is another one of my favorites. So that's 80 million years ago. Just let you watch it. Maybe you've already figured out what it is. Well, I guess it's written up there, so a few weeks ago, I was in Paris. I was giving a talk at the Institute Curie, and I asked everybody to do an estimate. And my answer was on the board. I'm not kidding you. I literally did this. So I go up there, and I did that. And so then the equation was on my hand. And at some point I noticed it was on my hand, and then I went like this. And so now the equation is on the back of my bald head. And at some point I had this realization like, oh, yeah, like the equation's right here. And so one of my colleagues is on sabbatical in Paris, and I saw him get his camera out, and I'm like, we got to reenact this. And seriously, I was like, this is such a great moment in public humility, like how stupid I could be. Anyway, so there's an example. I love this 80 million year trajectory. One other point, just in passing. I don't know how many of you have ever thought about Tasmania, but it's actually was never attached to Australia. It looks like it was, but it wasn't. If you watch the whole movie, which I'm not going to play again, it wasn't attached. Here's another example. The time series of Earth's biodiversity. I'll let you stare at this one for a sec, maybe just in silence. So that's the population of wildebeest over about a 50-year period on the Serengeti. So what I want you to notice is that there were maybe 200,000 wildebeest in 1955. By 1970, there were about 1.4 million, which is how many there are today. I will leave it unspecified as to what happened, but that's cool. And then, maybe some of you have seen this movie before, but this is enough to entertain you for a lifetime. So that's one of the cells of our immune system, a so-called neutrophil. The RBC refers to red blood cells. And what you see is that this neutrophil is hunting down a bacterium. Next time you get a cut and you have pus, that's sort of what should be in the back of your mind, is that this is teeming with activity as these cells are sniffing out, infecting bacteria and so on. And this is another one that I think is actually amazing. It's one of my favorite experiments ever. So let me tell you what's going on here. Up there is a cartoon of a single-celled organism known as Chlamydomonas. It's about 5 microns across, and it swims by doing the breaststroke. And what this experiment is, look at the lower left. Just stare at it for a sec. So what's shown here is time. This is the length of the flagellum. Red and blue are left and right. So what's being done is a laser is being used to cut off one of the arms. So what is this? What is the data telling us? You cut off my right arm, my left arm shrinks, my right arm starts to grow back. When they reach the same length, then they continue to grow. I don't know if in New Mexico, when you go backpacking, the question of Giardia is a question. Is it? Maybe Colorado for sure it is. But Giardia is an example like this, but it has 4 pairs of flagella, and each pair is different in length. It's very hard to understand the dynamics of how those things come to pass. So anyway, why do I tell you all of this stuff? I tell you all of this just because I want to comment on how important this idea of time evolution is. Doesn't matter what the field is. Finding out what happens to thing as a function of time is beautiful and interesting. So I got interested in what ChatGPT would think of the word evolution if I asked it how to use it in context other than biology. And what you see here is, I said not in the sense of Darwin, And so, in quantum mechanics, we know about the time evolution operator and so on. And so I want to continue going down this path of stuff of T for just a few more minutes before I cut to what I really want to tell you about, because I'm trying to set it up. I'm trying to remind us all of what all the dynamical equations that are part of the curriculum in physics are like. So I already mentioned at the top, F equals ma. That's great and fun and interesting. About, let's say 100 or so years later, Fourier came along and he said, there's something weird about this heat phenomenon. It doesn't really work as an F equals ma topic. And, he wrote down the heat equation. I'm going to say a few words about that in a minute. As I already alluded to, ideas about mass action. This is one of the simplest examples you could think of, which is ligand plus receptor come together to make a ligand-receptor pair. We can write down a dynamical equation for that, but we could do much more complicated examples. And I could write down population dynamics. So many, many possible examples. So I want to comment on Fourier for a minute, partly because I'm going to try to make an analogy, I suppose. So at the time that Fourier came along, he really was intrigued by this idea of temperature and heat, and whether or not the mechanical worldview of Newton would permit him to think about problems having to do with temperature and heat and its flow. And remember, this is at the time when people thought heat was a fluid. They didn't know that it was kinetic energy of molecules and so on. And so Fourier had this amazing book. It's just amusing. I don't know how all of you feel about the reviewing process. I'm not saying this in a snarky way. I'm saying it in a very serious way, which is that I'm not a fan of the righteousness of the review process. It's not something that was always true. I don't think it saves us from science, to have reviews, and it bugs me. In this case, Lagrange rejected Fourier. And I can give you a very long list of historical examples where somebody comes along and some other famous person renounces the effort. I don't find that very compelling. I just think it's cool. Page 478 of this book, right there is the green function for diffusion in 1D. That's the green function for diffusion in 3D in Cartesian coordinates. And just for kicks, what I'm showing you here is we took a cell and we photobleached the equation x squared equals 2 dt. And on the right, I'm showing you how you'd solve the diffusion equation using finite elements, because no amount of special functions that you learn in a mathematical physics class is going to help you solve this hard problem, let's say. But what I wanted to show you, just in passing, okay, I was saying, I think there's an analogy. Schrödinger, in his What is Life, I think made a very astute observation, which is, and he uses copper as his example. He says, if somebody came along and saw copper in coils, and you put a voltage, an AC voltage, and then you saw some motor turn or something, they might be like, well, that's weird. I thought copper was a thing that had a certain specific heat. But somehow I need a different law to talk about the behavior of copper when I'm talking about electricity and magnetism. And Schrödinger's point was, every time science turns its regard to a new phenomenon, new principles are figured out. And so Fourier is a great example of this. And I think in the study of life, there's such an opportunity for physics. It's not what can physics do for biology, it's what biology can do for physics, to paraphrase. So I just can't believe Fourier's book. So the first 30 pages of it, I recommend you go grab it. You can just go to Internet Archive, you can go grab an English translation copy. And in the first 30 pages, he has this whole discussion of Newtonian physics, all the effects like currents in the oceans, the jet stream, temperature gradients in the atmosphere, just all sorts of problems where he says something new needs to come on the scene here. So, he starts out by saying about 18 centuries elapsed before Galileo, the originator of dynamical theories, discovered the laws of motion of heavy bodies. Within this new science, Newton comprised the whole system of the universe. Then he says, but whatever may be the range of mechanical theories, they do not apply to the effects of heat. These make up a special order of phenomena which cannot be explained by the principles of motion and equilibrium. Now, we could argue about whether or not kinetic theory and F equals ma, blah, blah, explains thermodynamics. That would be to miss the point, I think. The point is, what are we going to do about these heat phenomena? And then, I love this part. He says, such are the chief problems which I have solved and which have never yet been submitted to calculation. I think there are a lot of problems about life that have never been submitted to calculation. If we consider further the manifold relations of this mathematical theory to civil uses in the technical arts, we shall recognize completely the extent of its applications. It is evident that it includes an entire series of distinct phenomena, and that the study of it cannot be omitted without losing a notable part of the science of nature. That sounds kind of obscure, but what I'm trying to say is, here's my phone, and I am not really into selfies at all, but let's see. I'm going into portrait mode, and then I do this, and here we all are. I just took a picture of some of the most amazing and exotic matter in the world, and to ignore it is to lose a notable part of the science of nature, in my opinion. I will never understand the weird relationship between the study of life and physics departments. Here's more examples of dynamical equations that describe all sorts of cool stuff, no doubt about it. And I love every single one of them. And I've taught every single one of them. I love them all. But what I'm going to tell you is that none of the 10 equations that I've just shown you is appropriate for thinking about a lot of biological phenomena. So that's the first part. I don't know if anybody wants to ask anything or interrupt or critique. Is there anything anybody would like to say thus far? Okay, I don't know. This is starting to feel like a bad sign, but we shall go on.
I have a quick question.
Great.
Do you recommend the primary sources? I mean, in terms of learning, is the best thing to do to first go to Fourier, or how do you think is the best way to learn? Where do you start?
Yeah, I actually do have an answer to that in some sense. And it's got two parts that almost contradict each other. But then again, I've become a fan of Whitman. Songs of Myself 51. You might remember this. I always was kind of pissed off about it. It's the one where he says, do I contradict myself? I contradict myself. I can contain multitudes. But I've come to realize there's a lot of merit in that. Out of sight, out of mind. Absence makes the heart grow fonder. Those are very contradictory and they both make sense depending on context. So, Niels Henrik Abel made a remark which I really, really love. Read the masters, not their pupils. He was talking about Euler. Like, Euler is the master of us all, he said. Here's the thing for you, and I'm happy to send any of you that send in now. If you look at the paper of Riemann on Fourier series, it's like butter. It's better than any textbook I've ever seen. And in it, he tells us about the Riemann integral, and it's very clear why and how. So Euler, if I want to learn about the gamma function, Euler is super clear. He's like, well, there's this thing called n factorial. That's awesome. What am I going to do if n's not an integer? I can make the histogram of n factorial. I had a grad student, super weird. I can't imagine a dad doing this, but on her 24th birthday, he sent her a note saying, happy last factorial birthday. So the thing that does raise the question of what is 4.5 factorial? And the answer to that is the gamma function. And if you read Euler, it's awesome. That all being said, so I'm a huge fan of read the masters, not their pupils, but for the real answer to your question for me, I'm just speaking for myself, is always the history of the subject and popular science. So, like in biology, there's a book called The Eighth Day of Creation. It is truly stunning about the history of molecular biology. That's where I started. When I started to learn mechanics, it was from I. Bernard Cohen. I don't know if any of you know that name, but he was one of the great Newton scholars. He wrote a little book called The Birth of the New Physics, and even an idiot at the age of 18 who didn't know how to remove parentheses from A minus B minus C minus D, i.e. myself, I really came to understand what was going on. George Gamow, 30 Years That Shook Physics. It's an amazing book about quantum physics that I learned a ton from. So personally, for me, I'm slow. I have to start at the beginning, and I need to know context. Like, I don't understand how it is. Again, I've got all sorts of personal opinions. I'm sorry. I really don't like giving talks for this reason, because I feel exposed, but I don't understand how we make do without knowing the history of our subject. It just makes zero sense to me. So I guess that's rather evident. So what I wanted to talk about is this idea of how do we make generalizations? So I love the fact that Carnot said, yeah, there's an English version of a heat engine, there's a German version, there's a French version. And at the end of the day, I can boil off the fat, and there's a very simple set of ideas, the Carnot cycle, that describes that. Good. I view Shannon as being exactly in the same department. So he comes along and he says, you can talk by telegraph, you can talk by wireful phones, or you can do Wi-Fi or whatever. But the question of error transmission and communication is there's general principles in play. And so now to get, even though it's 20 minutes in, I can get to the meat of what I want to say. So this is quite an amazing book by Mark Kirshner and John Gerhardt. And it's it would surprise all of you, I think. So I teach freshman biology for haters at Caltech. Every kid at Caltech, I'm not saying I'm a fan of this, but everyone has to take 3 terms physics, 3 terms math, 2 of chemistry, 1 of biology, 1 of CS. And I teach the freshman biology for physics majors, engineers, whatever. They colored mitochondria orange in high school. They're convinced that biology is mindless, memorization, unprincipled, etc. And often if you look at the organization of a textbook, you might conclude that that's true or that it's factually oriented. These guys organize biological thinking in a completely wild way. And their chapter 4 is what my talk is about. Mark Kirshner and I are working together on this, and I really, really love it. So chapter 4 is called The Exploratory Behavior of Biological Systems. And the assertion that I want to make, and it's done playfully, like I'm here today, not telling you I've finished something, I'm not telling you that I've made a big discovery or somebody else did. It's more like, what is the reality of what I'm actually doing with my time? Because at the end of the day, time is precious for each of us, in my opinion. There's very little of it. And so you vote with your actions. And my actions are, I think this is damn important and interesting. So what is the idea? The idea here is that biology has its own unique approach to dynamics. The first example of it is Darwin's theory of evolution. But actually, I'm going to argue that's a special case. Variation and selection is much broader than just evolution in the sense that you're used to it. And here I give you 6 or so examples, and I'm going to focus on several of them, but let me just kind of in passing give you a thought about this. So if you go to the Galapagos, you go to the islands in the Southern Ocean, the albatross leave their young, they go off and fly 5,000 miles, they come back and they feed their young. Penguins in the Southern Ocean leave, we know, we tag them, we know how fast they're swimming, where they are, what depth they are, and the frequency with which their mouth is doing this. And what we find is the paths, the exploratory behavior that they undergo. Every cell in your body is within 100 microns of a capillary. That is not done by some design, it's done by exploratory growth. Same goes with, for example, the growth of neurons. And so all of these are examples of exploratory dynamics, and I'm going to try to illustrate that. So what we're going to watch now is a little video, which I both love and hate for reasons that I'm going to describe. And the idea of this is how are proteins synthesized? Proteins, just a reminder, the macromolecules of the cell are long chain molecules, polymers. The nucleic acids are the conventional ones that we're all used to, A's, C's, G's, and T's. But that gets turned into a different language of 20 amino acids. And the machine that does that is the ribosome. So what I'm going to show you is this process. I think there might be sound, but the sound doesn't really matter. Sound effects are annoying.
When the mRNA is complete, it snakes out of the nucleus into the cytosol.
Well, so that thing's an mRNA molecule. That's basically the bright sphere is the
Then,
nucleus.
in a dazzling display of choreography, all of the components of a molecular machine lock together around the RNA to form a miniature
That
molecule
object is called the
ribosome.
ribosome.
It translates the genetic information in the RNA into a string of
here's my
amino
hang-up.
acids that will become a protein. tRNA molecules, the green triangles, bring each amino acid to the ribosome. The amino acids are the small red tips attached to the tRNAs.
So
There are different tRNAs for each
Here's the problem with this video. There are 20 wrong tRNAs for every right one, right? In other words, the tRNAs are holding amino acids, and most of them are not the right one.
Yeah.
The movie shows every tRNA that arrives as delivering the right amino acid, and it bypasses one of the most amazing things about biological systems. I'm going to bring it up in a little bit, but let's talk about DNA replication in your cells. So if this were the diameter of DNA, then the machine that copies it is the size of a FedEx truck. It's traveling at the speed of a jet airplane. It's delivering its boxes every 10 centimeters. It makes its daily journey in 40 minutes, and it makes one wrong box delivery every 3 years. That is the accuracy of DNA replication. 1 in 10 to the 10th error rate. So there's something going on here. This thing has got to figure out how to reject the wrong ones. It's exploratory. So here I'm showing you a little version of this, and I want you to key in on the words variation and selection. Those are the words we would normally use in the theory of evolution, but I'm using it in a very different context. So here's the ribosome, and this is the mRNA. The colors correspond to which amino acid is going to get added. And the point is that there's this whole reservoir of both wrong and right tRNAs, but the wrong is vastly bigger than right. And the little Maxwell demon is sitting at the door. You knock on the door, and if you're the wrong tRNA, you're sent away. For this to happen, free energy has to be expended. And every time it's the right one, the door is opened, the next one is added on to the thing. So that's an example of what I'm referring to as exploratory dynamics. So now what I want to do is, instead of talking in big picture terms, I want to give you a concrete example, which has to do with chromosome segregation. So here's my example, and let's watch this movie. Hopefully you find it beautiful and interesting. So what you see, the blue things are chromosomes. The green stuff is a filamentous polymer known as microtubules. And the way this works is the microtubules form a football-shaped object called the spindle spontaneously. They grab onto the chromosomes. When the correct number are attached, the cell is given permission to divide, and it pulls them apart. So that's the essence of the thing. Like I said, I told you this earlier, but now here's the figure that goes with my claim. So if you're an engineer and you want to build a railroad between Boston and New York, you know how this works. You're systematic. There's a budget. You order things. You know where the thing is going. They're going to grade the earth. They're going to do all these things. The bottom is the actual way that this works in cells. And I want you to be saying to me, isn't that inefficient? Isn't that somehow screwy? Doesn't that cost a lot? Clearly, that mindset about efficiency is misguided, in my opinion. And we can try to quantify that. So here, once again, the mechanism is one of variation and selection, and I just want to show you a movie of just trying to prove to you that this is the way that these microtubules work. That is actually what you will see in a microscope. They grow, they shrink. They grow, they shrink. And only if they hit their target do they stop growing and shrinking. They hold on. I feel like, maybe, well, we'll come to that in a minute. I want to just say, so in the lab with Matt Thompson, what we've been doing is we've actually been building these structures in a way that we can control using light. And I'll just say quickly what I mean by that. So these structures are built up of these green filamentous polymers called microtubules, which I already told you about. And then there are little molecular motors. And in case you're not used to thinking about molecular motors, they're, say, 5 to 10 nanometer objects, which actually walk along the filaments. Sometimes they carry cargo, like in our neurons. They're carrying cargo out to the far terminus of our cells. But they also do things like contraction, and they form structures and so on. And the trick that we have is that we have a light dimerizable motor. What that means is when we shine light at it, the motors come together, and now they cross-link the microtubules. So what you're going to see in this yellow disc is us shining the light. And when we shine the light, The microtubules self-organize spontaneously into these aster structures. We turn off the light, the aster structure goes away. There's many different things that we can and have done with these systems, which I show you here. So what you see here is a bar of light. Here there's two disks which are being moved, and you can see the aster follows the disk. And this one is two disks and a little bar connecting them. And so these things self-organize in a way that we can examine quantitatively. So the thing I would say, and I do say on my slide, is that these movies trivialize error elimination. So, you know, sometimes, let's say a woman over the age of 35 gets pregnant. One of the things that will happen is that mom's blood will be sequenced in order to find out whether there's trisomies. In other words, extra copies of chromosomes. Some of them are lethal, some of them are not, some of them lead to things like Down syndrome. But this partitioning process must have high fidelity. And I wanna say what I mean by that, because it's really interesting. So we humans have 23 pairs of chromosomes. All of our primate relatives have 24 pairs. So if you buy the idea of evolution, you must think that one of our pairs, what happened? One of our pairs of chromosomes must have merged. That means that in one of our chromosomes in the middle, we should see evidence of the ends prior to the merger, which we do. So that's something that DNA sequencing led us to understand. But now I want to focus on this thing about 23. What this means is that those microtubules that I showed you, they have to know how to count to 46. Not 45, not 47, they have to count to 46. And there's a beautiful experiment that was done by, this thing about Caltech undergrads, because I gave this talk to the Caltech physics faculty. And it's just, I find it kind of cool that both of those students, I knew them when they were undergrads, and they got together at Harvard just by knowing each other. And they did this cool thing, which is the details of my slide don't matter very much. What I want you to take away from it is the top row shows you that they can count the number of connections and the number of divided chromosomes. So when they do it, here's the error rate. 0. If they ask the cells to divide before they're ready, this is the error rate. In other words, it's not perfectly 46. And what that amounts to is interrupting this exploratory dynamics that I was telling you about. In other words, if you interrupt before the train between Boston and New York has had a chance for all the tracks to meet each other, then you will not have a proper railroad. You won't have proper chromosome segregation. So what I thought I would do is, maybe just tell you a little bit about our attempt to have an interplay between theory and experiment in the context of these problems. And I'm going to tell you about a little toy model in 1D, just to set notation, and then a full 3-dimensional model. And then I'm going to tell you about how much it costs. Because this notion of efficiency, I think, is really interesting. And there's discrepancies of order 10 to the 9th between what we think and what we see.
Ooh.
And I like that, because usually if you have a big factor like that, it means you don't know what you're talking about. It means you're on the wrong track. And this whole efficiency thing, I think, is a wrong track. So, how to think about this? So, the way that I would want you to think about this is that in this toy model, the green circle is a nucleation center for these filaments. They grow for a certain amount of time, and then they suffer a catastrophe, and they shrink again. And we know the probability that they will live long enough to reach the chromosome. So that probability I'm going to call PS. So what I'm showing you here is that we can sum over all possible trajectories. Here they are. First try, I win. That's trajectory number 1. Trajectory number 2 is I try once, I fail, and then on the second try, I succeed. And then the third one is try twice, fail twice, then succeed, fail 3 times, succeed. You can sum over all those possibilities, And you can calculate the mean time it takes. And that's the equation that I show you there. That's more or less as much as I want to say about it. Now let's be a little bit more realistic. The chromosomes actually, the microtubules can grow anywhere on the unit sphere. So there's a probability of them going in the wrong direction and a probability of going in the right direction, which I'm calling FR and 1 minus FR. FR for right direction. And so here again, we can calculate the mean first passage time in order to find the chromosome. And what I like about this is that really amounts to, once again, failure, 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 always ending with success. Exploratory dynamics, if I think about the probabilistic structure of the trajectories, is always the same. Fail, 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 always ending with success. So if you go through such a calculation, what you'll find is that there's an optimal rate at which you should start over. There's an optimal reset frequency, if you want to think of it that way. So there's a best time to capture. I think that's interesting. It leads to some predictions about how this depends on cell size. And that's the kind of thing that we're trying to think about now. So let me just say a few words about the energetics and then I'll stop and maybe entertain some questions. So I'm very amused by something, which is that in the early 1970s, these two guys were thinking about the same thing, but in very different contexts. They were both young guys at Princeton at the time. So Hopfield, hopefully many of you know him. He's a fascinating guy. And in the early 1970s, he was wondering, why is there energy consumption in protein synthesis? And the reason he was thinking about this is the dogma at the time was that the way you discriminate between right and wrong tRNAs is just by equal Boltzmann, e to the minus beta delta epsilon, meaning do the three nucleotides match up between tRNA and the mRNA. If you use Boltzmann statistics, you find the error rate is 1 in 100. It's just way, way too high. So he was like, what's going on with this extra energy consumption in the process of protein synthesis? And it led him to this paper on kinetic proofreading. Kirshner, at the same time, was wondering about something about these polymers. And what he ended up telling Terrell Hill to convince him to work with him is he said, look, any equilibrium polymer, you have no hope of lifting a weight with it. But if you take a microtubule and you could and you had a way of attaching a string to the end with a weight, while that microtubule is polymerizing, you can lift a weight. That will not happen with an equilibrium polymer. It violates the laws of thermodynamics. But because GTP is being consumed, these polymers can do work. And so we've been very interested in the energetic consequences and costs of this exploratory behavior. So I'll just quickly say something, and you and I talked about this a few minutes ago, and I really loved it, which is it's very interesting to understand what is it about carbon, nitrogen, oxygen, hydrogen, such that when I look at that fool in the selfie, I'm so different from a hunk of carbon, hydrogen, nitrogen, whatever, that's inorganic. What is it that gives rise to this thing we call life? And the way I want to think of it is that there's all these biological batteries. So the most fundamental one of all is just there's this thing over there called the sun. It's none of my business. It's just there. And we're just being flooded with energy, 1,000 watts per square meter. And it can be used. And interestingly, it can be used to make sugar. And sugar is an amazing thing. It's got 1,200 KT worth of energy per 6-mer. It's huge. One photon is like 100 KT. That sugar is in turn converted into concentration gradients. Those concentration gradients are maybe worth 1 ATP or 20 KTs, something like that. And that hydrogen ion gradient turns a little molecular motor to produce ATPs. I'm always amused when I get on an airplane. I don't know how many of you, if you sit in the front of the plane and you look at the engine, there's a spiral on the jet. And if you go out on, even when you get to the runway, it's still recognizable. I always test this out. When the pilot goes to full thrust, that is 6,000 RPMs. Divide that by 60 seconds, that's 100 hertz. That is precisely the speed with which this molecular motor rotates. And I can't hear that without being like, what? You gotta be kidding me. 100 hertz, the speed of a jet engine. That Right now, in my body, your body, all of us, we're synthesizing like 30 kilograms of ATP every day with little molecular motors that are spinning at the speed of a jet engine. I don't know, I don't want to take that for granted. I just don't. And if you do, that's cool, but I don't. So what we wanted to do is we wanted to measure ATP consumption in space and time to try to learn something about the cost of exploratory behavior. So I'm just going to tell you a little bit about that, and then I'm going to stop. So we have these microtubules, we have these motors. If you like, just think of it as we have engines. And our question is, how much fuel is being consumed as a function of position and as a function of time? And the way we measure it is using an ATP-sensitive fluorescent reporter. So in other words, we can calibrate how much ATP there is in absolute units, micromolar or number of molecules per micron cubed or whatever. This is the work of Anna Duarte. And so we have this calibration curve, and this is what an experiment looks like. So what you see on the right is ATP in absolute units of micromolar, and what you see on the right is the aster. So if we do that a bunch of times, we can figure out how much ATP is being consumed, how much fuel is being consumed as a function of position. And the top graph right here, let's look at this. The y-axis is concentration of ATP. The x-axis is distance from the center of that little star. Time is coming down. And so what you see is that ATP is being used up, and there's a gradient that's formed, which is interesting in and of itself because ATP is small and diffusing. So there's a dimensionless parameter that's the relative rate of diffusion and consumption at play. So we have this gradient. We can go through various things to try to calculate it. I won't belabor that. But what I want to say is we basically can measure the power. And so my final volley in this discussion is just to say to you, we could ask the question of what is the energy being spent for? So one thing you could imagine is you have all these microtubules, it's homogeneous. And because of the motors, it gets brought into a spherical geometry. And so you might think that the PV work is what the ATPs are being spent on. Another idea is that the microtubules are being dragged through a viscous medium. So maybe there's a drag force that's in play that's interesting. There's other things. I will just touch on them real fast. So first, let's look at the units here. The units are something like 10 to the 8th ATPs per second. That's the power in one. In one of these asters. In other words, we're looking under the microscope and we're measuring on the order of, let's say, 1/10 of a billion being consumed per second. And now what I'm going to do is I'm going to work out the power budget of these various processes. So just for example, I have this uniform collection of microtubules. It collapses into this sphere on a time scale of like 10 minutes. If you just use logarithm of V final and V initial, you can figure out what the PV work is. And that leads to power 10 to the 5th smaller than what we measure. So it seems like the ATP is not being spent on PV work. Next idea, which is drag. So here, what's the dumbest thing you might do? You might pretend that that cylinder is actually a sphere. Clearly that's an upper bound, it's way more than it actually costs. And if you just use Stokes drag, what you find is that it's a very small number. I first learned that, I don't know how many of you were here, probably not very many when Carlos Bustamante used to be a professor here, but when I first learned about optical traps in the context of biology, I was always thinking, wow, you have this 5 nanometer motor, it's pulling around a 1 micron bead, there must be some huge drag force. But it turns out, if you calculate it using that drag law, it's really nothing. It's femtonewtons in comparison with piconewtons. So it's 1,000-fold down relative to the actual measured values. And I think, rather than going into too many details, I'll just say the last thing is that if you work out the cost to maintain the gradient, there's a gradient of motors. And if somebody wants to ask me about it, if you work out that, that's closer to the power scale that we actually measure. So that's basically what I wanted to say for the day. I don't know if it worked, but let me try to summarize. So first part, this part I feel good about. I feel what I'm going to say is defensible. I like the idea of thinking of myself as being here in an oral candidacy exam. And if you guys were like to question me, I would feel okay about defending stuff of T. I would feel like I could tell you, yeah, come on, man, there's this thing F equals ma, you know that. There's a heat equation, there's Maxwell's equations, there's lots of theories of how systems evolve in time. So that was the first point. The second point was more hypothetical. There was an argument, there was a claim, which is variation and selection, which we first learned about in the Darwinian sense, is actually much bigger than just the theory of evolution. Our immune system is constantly making bad antibodies. And the whole game is, the first thing that happens is we ask our antibodies, self or non-self. You want to make sure that your antibodies do not recognize you, because otherwise you will have autoimmunity, you know? So 20% of you in this room are going to have hypothyroidism or something like that, 10 to 20%. And so that's your immune system attacking your thyroid. It's bad shit, excuse my language. I just know from a personal point of view. And so that's an exploratory dynamics. Most of the antibodies are rejected. So I'm excited about this idea that the search of transcription factors for their binding sites on DNA, the search of microtubules for chromosomes, the development of vasculature so that every cell is within 100 microns of oxygen, and foraging, albatross searching. There's all these examples which suggest a different kind of dynamics, which is largely independent of initial conditions and which cares about final state. And if I were to use teleological language, and people are super triggered by this, the dynamics is purposeful. There's a function. There's a reason for the dynamics. I can't say that there's a reason. The moon is not, you know, Aristotelian dynamics was like, the thing wants to be at its center. And that sounds pretty annoying in retrospect. But saying something has purpose in a biological sense, I think is reasonable. There's a purpose. The beating of my heart is not about, you know, the beauty of the deformation. It's about pumping blood places. So the oxygen is in the right place. So anyway, that was the second point, was this notion of exploratory dynamics. And then the last part was just to say, I think it's very interesting to ask, is there a mathematics that's going to sit over all these different examples that in retrospect we will say, oh, wow, that's a principle. There's many examples that look the same if viewed from the correct perspective. And two examples that really catch my eye, I don't know how all of you felt about it. The first time I learned about harmonic oscillator, I was just like, there were many things that went on for me. What's with these physics types turning sine theta into theta? You know, like what's up with this Taylor series obsession, you know? Then the next thing was, why are they so obsessed with like frictionless mass spring, blah, blah? I was wrong, you know? When I learned about RLC circuit, and then I'm like, oh my gosh, you know, the same equation describes the mechanics of a mass spring system in RLC circuit. Then I say to myself, wow, this harmonic oscillator thing has got legs. That's really cool. And that's what I'm hoping we could find in this case, something like that. The last point was about energy. I just hope you will remember the example about the trains between Boston and New York. Just think of that when you think about biological dynamics, because somehow, maybe the way Mark Kirshner puts it is, you know, well, why would the cell spend so much energy? Because it's better than dying. You know, somehow, if you don't segregate the chromosomes correctly, it's lethal. So anyway, that's my spiel. I really had fun today talking to people. It's really interesting. I just wanted to say that, you know, it's been just one of the signature privileges of my life to hang out with. I have no idea why Mark wants to hang out with me, but we're trying to write a book together. He is a super special scientist. You know, he's made major discoveries, but I just love hanging out with him. Yannick Kondev is the guy I've written our book, Physical Biology of the Cell with. I highly recommend you guys have him out here. He's a really great expositor. And then Anna Duarte, Gabe Salmon, and Sarah Madavi are the ones that kind of crazily joined us in this very speculative endeavor. Like I could have told you about the things we're doing that are more normal, but somehow I thought maybe it's more fun to hear like really what I'm excited about, but I'm not sure it's going to lead anywhere. I don't know. So on that note, I'm done. I hope I didn't take too long.